Hey everyone. Alright. I just figured I'd test this out. See how the audio works. See if the audio is too low. Oh, that's good. You can hear me. Why so nerd? Yeah, probably. I'll take that. Are we learning about computer architecture? Maybe soon. Maybe not. Maybe not this stream. So, what I'd figure I'd do, I don't know, let's go over some of my ideas that I had. I had a couple ideas. I can't show a face cam. I'm in my lab and I don't have a webcam. Oh. Yeah. No webcam right now. The webcam doesn't exist. Oh yeah, I gotta get mods or something, right? That's something that people do. Maybe I'll just have complete control and just, no talking in the chat. That would be fun, wouldn't it? That would be mod me. Okay, make my volume a little bit higher. Yeah, I can do that. I know how to do that. That's a slider bar. I can do that. Turn on sub-only chat. I don't think I can turn on sub-only chat because don't you have to have a certain number of views and followers before they even give you an option to subscribe? Okay. If you're talking, you're not learning. Well, maybe. I talk to myself a lot in my lab. Probably pisses off my lab mates. Engineering Today. Why is your name Engineering Today? And not Why So Green? Because no one knows what I do if I put Why So Green. It breaks your immersion. Okay. So ENGR is one of the more common abbreviations of engineering for most universities for registering for courses. Usually it's like ECE or ME for mechanical engineering. For places that have a single engineering program, though, it's usually just ENGR, or for general engineering courses, it's ENGR. So it's the shortest engineering today that was available, because ENG today wasn't available. That's why it's ENGR today. How do we know you're even actually legendary chatter? Why so green? You don't. It's all a surprise. Okay, so let's see. Why not engineering tomorrow? You stuck in the present? Yeah, because I'm realistic. It's the reason why I don't watch TED Talks, is because TED Talks do two things. They either present a technology that already exists that isn't financially viable, or they introduce something that already exists, or that isn't viable on a practical sense. It's like I don't know if they've done anything on it, but it's like high bandwidth memory. It's like, oh yeah, if you just put high bandwidth memory everywhere, it's like, oh, all the performance shoots up. Except Nvidia can't even get enough high bandwidth memory to support, making all their cards. They run out. So that's not really a great great place to get information from. Okay, so on to the more pseudo-serious, not serious, onto a different subject. So, let's see. Let's see what I can do. Okay. Okay, now you should have a nice pretty thing for me to draw on. And I get to learn how to draw while not looking at what I'm drawing, which is nice. I like doing that. I'll zoom it in again. Linux, where's Arch? Not on this machine, because this is a lab machine that requires Ubuntu for things to work. And I could use Arch, but that would mean I would have to support it myself on Arch. And why would I do that? Okay. So, let's see. Oh, superior Linux. They're just different distributions. Like, Ubuntu works just fine. High taskbar breaks immersion. Good. I want immersion to be broken. Okay. Okay, GNOME is the best. GNOME versus KDE. The streamer is such a nerd. Yeah, pretty much. I mean, don't you have to be to get a PhD? I think you have to sign a contract saying that you accept the terms and conditions of it. Okay, so I was thinking I'd go over some of the books that I plan to go over for streams. So I'm open to suggestions, but these are just the things that I think are interesting. So there's a pretty interesting book that's called Programming, what is it? Massively Parallel Processors. And this is Kirk and who? That's a pretty good book. That's basically from NVIDIA. It's from I don't know where Kirk is from, but Wenmei Wu is from UIUC, and he has his entire he basically, this is the gold standard book for programming NVIDIA cards using CUDA, which is, I forget what CUDA stands for. It's something Unified Device Architecture or something. So I want to do this one. So this is going to be, this is going to be GPU programming. So other than that, I mean, you have to do a computer. If you're a computer architecture person, you have to do a computer architecture book. And if you're going to do a computer architecture book, you've got to do the only computer arc, a quantitative approach by none other than Hennessy and Patterson. So that's going to be... See, it's so funny saying this because that's like your graduate level book in computer architecture. But everything in that book is from like the 80s. But you learn so little in undergrad that that's about as far as you get. Well, not as a grad student. I mean, you have to teach the stuff to yourself, whatever field you go in. But as far as coursework, that's about as far as you get. Well, that's not true. There's usually one. So the problem is with architecture is once you get to a certain point, all your time basically gets caught up in memory consistency. The consistency is just such a hard problem. I mean, you could dedicate 10 classes to consistency. But if you're dedicating 10 classes to consistency, you're wasting your time because you should be doing research or something. So, yeah, that's fine. Okay. So those two are for certain. Yeah. Debated into learning actual stuff right now. Maybe. I don't think you're learning anything too much. Maybe you're learning a little bit about what are the prerequisites for this stream. I'm learning Algebra 1 at the moment. There are no prerequisites for this stream. If you watch the stream, you're going to get something out of it. Like here's a very interesting little tidbit about architecture. Is that did you know that the ALUs, oops, what was that? Did you know that the ALUs within your processor generally run at about double the frequency of the rest of the processor? They basically double pump ALUs in processors because, you know, math is fast versus, you know, memory, which is slow. ALU, arithmetic logic unit, it's the thing that does the math. Just add, subtract, multiply, divide. Here's another fun fact. If you're basically going to put, you know, what takes as far as like an arithmetic operation, not talking about, you know, some special, so usually you have two things. You have like special functional units, and those are going to things that do like square roots, right? And logarithms, the very dedicated things. But so for general purpose things, you know, add, subtract, divide, multiply. So if I'm remembering correctly, because I took a grad course on this when I was still an undergrad, and it was all in computer arithmetic. So if I remember correctly, how long it would take to do like an add in like a modern processor, and it's like 1 to 2 clock cycles, extraordinarily quick. Those circuits have been optimized. They've super optimized those circuits. Multiplies. Well, think about what a multiply is. It's just a bunch of adds. So I think multiplies, it stands to reason 2 to 4 clock cycles you can push out something that's a multiply. A subtract is the same thing as addition. So same thing, 1 to 2 clock cycles. But divides, divides I think take like 500 to 1,000 clock cycles. They're incredibly slow. Yeah, they're something. Maybe we can go into that some other time. That's always fun. Kind of going why divides are so slow. Yeah, that was a really interesting part of that class. Why so slow? Well, because adds are fast. Circuits to do addition are very fast. Circuits to do subtraction and having to do the checking to make sure that you're within a certain range, because if you think about how a computer would do something like addition, if you just have this, let's just have this like black box, and we have like we have three inputs, which is going to be A, B, and C in, and then we're going to have two outputs, which is always going to be your sum, and then let's call it S0, and then your carry out, like C0, right? So in here, you're only going to have, let's see, what is it going to be? It's going to be 2, 2, 2. You're going to have a max gate delay of 2. It's 2 gates to calculate everything, to calculate the carries and to calculate the sums. It's only 2 levels of gates. We'll just use that arbitrary, because I'm not going to go into time how long it takes to get through a gate. And so this is very, very quick. And so when you start chaining these together, you can do very basic things where, basically you just shove a bunch of these next to each other and just feed the carry outs into the carry ins of the next little adder block. And then you wind up with this propagation delay of, if there's only carries in the circuit, or if everything generates a carry, it's just going to carry over on and on and on and on. And so that's going to be your critical path. But there's faster ways to do this. So there's things called carry look-ahead adders, which maybe we'll talk about another time. But carry look-ahead adders are ways of predicting if there's going to be a carry later on, which speeds up addition a ton. And like I said, multiplication is just addition. If it's 3 times 5, it's just 3 5 times. So that makes sense. Let's do a different color. Okay. So those 2 books, like I said, the computer architecture one and the GPU programming, and it's also a little bit of architecture. Actually, it's quite a bit of architecture. That's the fun thing about GPU programming versus regular programming. So when you're writing most code, depending on the level of abstraction you're working at, you don't have to care about the underlying architecture at all. Now, if you're writing super optimized HPC code, which is high performance computing code, yeah, sure, you're going to be worrying about tiling things out in memory, and you want to know everything about the architecture. But most people writing code don't care about the underlying architecture. They want to write code and they want it to run. They don't care what's happening underneath, really. So GPUs don't work that way. You can't program a GPU unless you understand what's going on underneath. And that's not even that's not even an exaggeration. You have to specify things like how many threads you're launching, and however many threads you're launching and thread blocks you're launching, and the size of these grids of threads that you're going to be putting on, or these thread blocks that you're going to be putting onto the GPU. Every architecture has different limitations for GPUs. So you have to manually specify that. Also, you have to manually manage memory. Isn't that fun? Isn't that just great? You don't get any help there. So that's fun. Yeah. So that's why GPU architecture is interesting. Okay. So this is the open time. This is what are we going to learn? Life ain't easy. Yeah, that's true. Okay. So, what topics should I cover? I should note I'm referring to computer engineering, maybe some computer science. Some people get that confused and think I'm a computer science major. I am not a computer science major. There's a lot of differences between a computer science major and a computer engineering major. Both are fun. I do a lot of computer science work. And some schools, this is actually within a computer science field, but that's usually undergrad. It doesn't matter what field you're in grad school. It doesn't matter. Whatever you're researching is going to be found in some certain area, and so it just matters if you find that area. If I were you, I would do intro college courses. Yeah, intro college courses are boring, but I did make a YouTube video on intro college stuff that got like 20-something thousand views, and it was on something that, I did, I guess now it's been 4 years ago, maybe 4-ish years ago. That was the logic. I'm planning on doing that, so that's another thing. It's another book, Contemporary Logic Design. So that's going to have some Boolean algebra. It's going to have state machines. And it's going to have logic gates. So this is like the first course in electrical engineering. What is inside of a resistor? Is it just a bunch of wires? Well, I hope not, because wires are generally metal, so that means that it would just short immediately. Wires do have resistivity. They do have some resistance, but not when they're that small. Maybe you could do 1 day a week for questions only, when people could ask specific questions they have trouble with. That was part of the idea. I mean, like I said in that intro video that I did, I want it to be, a very interactive stream. I want to take a lot of suggestions from people as far as what they want to learn. So that can be things from, hey, I'm having trouble with this computer engineering thing. Like maybe something dealing with algorithms, maybe something dealing with computer networks, maybe something dealing with, I hope architecture. I like architecture. That's what I do. That's fun. In fact, if we could have an entire question day dedicated to architecture. But isn't this content much more suited for YouTube? Yes, that's why it's all going to be on YouTube. That stuff's going to be on YouTube. So in that intro video, I'm going to have a bunch of series called Page by Page. And so it's going to be page by page for each of these books. And so it's going to be like page by page for Contemporary Logic Design. And it's going to go through the entire book. And so what I want to do is start a couple of those, probably like 3 at a time, and do maybe 6 videos a week or something, because I'm dedicating about 3 hours a day to this type of stuff. 3 hours max, I should say, for this type of stuff. And so, yeah, I think I could do 1 video a day and then not do a video the other day. Like Saturday or Sunday or something. So I figure I do like 2 videos on each book per week. So it'd be like 2 videos on computer architecture, quantitative approach, 2 videos on computer networks, a systems approach by Peterson and Davey, and then 2 videos on contemporary logic design per week. You should do one on writing a proposal letter for grad school. What is a proposal letter for grad school? I don't know what that is. Is that... Are you talking about like a grant proposal? Or are you talking about like an entrance letter? Or essay? I don't know what a proposal letter is. Am I proposing? I can't propose to the university. I already have a fiance. I don't think she'd like that. Man, I feel like I'm playing Xbox or PlayStation for the first time in forever, because I keep getting the Twitch achievements for first stream, having a stream for X amount of time, X amount of viewers or something. So what I figure I do in the streams is mainly go over things like research papers. And maybe I'll go through a research paper tonight. I have one that I read fairly recently that I thought was pretty interesting. Wasn't necessarily too novel, but... Or, no, I shouldn't say that. It was novel. It wasn't something terribly complex, though. Which is not a bad thing. I mean, if you look at a lot of the major innovations of computer architecture, looking at them now, most people, I think, would go back. Like, if they had no context of, like, when this was, proposed, I think they'd look at a lot of papers and they go, wow, this is stupid. Everyone would have thought of this. Like victim caches. So victim caches were something thought up by Jopi, who I think was a professor at Wisconsin-Madison. And basically the idea is, I've got it. Let's have a smaller cache underneath the cache, so that if the cache misses, we have a very small cache for it to not miss in. I mean, of course it works. You basically added a tiny cache. But yeah, so I figure on this stream, I'd probably... Oh yeah, L3, L2, L1. Yeah, sure, but you have victim caches in there too. You got caches that aren't in that hierarchy of L3, L2, L1. You get caches everywhere. That'd be an interesting video. Or maybe that'd be better suited for a stream. So, I got off track. So basically, YouTube's going to be where I'm going to do most of the videos that are, the prepared content on specific books and teaching. And then maybe I might do a stream. I might stream 1 or 2 of those, just if it's on a topic that has a lot of questions. That way I can answer them immediately instead of just going through and seeing 1,000 people asking questions on something. That might be better for that. But no, what I want to stream more of is I think probably research papers. Research papers are interesting. Not to mention they take a lot of time to go through. So let's see. Let's see what I'm going to do on stream. Ideas for stream. So 1. Let's have research papers. 2. Q and A. What else? What else am I missing? Research papers, Q&A. That's probably fine. I don't have a ton of time. Yeah, I think just maybe fun stuff. Ooh, I got it. Demos. Breadboards. Why would I do breadboards? That's actually an argument I got into I actually got into an argument with somebody over breadboards, and it was over undergraduate education, and it was all about, this course that made people what did they make them do? They made them do things like, blink LEDs and stuff on breadboards, and it's like, really? It's 2018. This analog stuff, we're past this. It's this very interesting idea, and that's okay. So you're in 1950, right? Let's say you have this big stack of stuff to learn, right? But before you start doing any research, okay. So let's move forward in time to 2018. Well, there's been a lot of research since then. That's pretty interesting. It seems like the basics require a lot more stuff. Oh, well, here's another interesting thing. All of this stuff hasn't been done in 30 years, so why are we still learning it? That's interesting to me. Now, maybe for some context, it's nice. And for certain things, yes, you can't just abstract everything away. But, I mean, this isn't nobody would agree that this is a scalable way to move forward. It's just like the reason why people love, Python with TensorFlow. It's because you don't need to know anything. You just go in there and you plug and play. And people like tools that are easy to use. It sounds like a knock on the controls field, and I don't mean it as a knock on the controls field, but a lot of work in controls now is basically making controllers from or using machine learning to make controllers, because PDEs are hard. Partial differential equations, those are hard. Why do I want to try to solve some ridiculously complex problem when I could just shove TensorFlow at it, or just throw some data and throw some outputs, and if it works, it works. Great. I don't care how it works. If it works, build my circuit. What's your circuit? What does it even mean? Is it an integrated circuit? Do you need to write some Verilog? Verilog's easy. It's not easy. Some stuff in Verilog is easy. Intro stuff in Verilog is easy. A lot of people take an intro class in digital design and we'll have the AI build it. Yeah, that's already being done to some extent. I mean, so if you have, most people in here probably have not done, any kind of PCB layouts before. PCB layouts are something that really gets you to appreciate how far we've come and things like path planning and routing, because I had some project where we were building like a 3-stage audio amplifier, and we were actually building a piece. We were actually designing a PCB, and we were gonna solder all the stuff onto it and demo it. Fun. But with that, you only have about, I don't know, it was like 20 components total, like some caps, some resistors, a button or a switch, and some op amps or operational amplifiers. It can be really hard to automatically route the traces for just 20 components. Now, most components have, or when we're talking about through-hole components, op amps have 6 legs, and then pretty much everything else is 2 legs, right? Now, imagine this. So we used a Spartan 5 FPGA we used a CSG. The actual chip was a CSG 324. It was already on a board. This wasn't something I soldered. It's a BGA, which is a ball grid array. So unless you have a pretty good setup and are pretty proficient in soldering, you're not going to solder that yourself. So these were some pre-made boards that they sell. They're just development kit boards that people use everywhere. And so this one chip, this one FPGA, this Spartan 5 from, what's the company? It's the Xilinx. It's a Xilinx chip. CSG 324. It has 324 pins, which are basically the balls underneath the chip, the little solder balls. So, okay. So, conservative estimate for the board that I did, let's just pretend everything had 6 legs. So 20 components times 6. Okay. 120 things to route someplace. Okay. All right. That one chip on that board had 324. So imagine having to automatically route that. And just for reference, we used, what's it called? It's Cadence's board layout tool. PSpice, you do the circuit diagram, and then you import that you import the whatever file that outputs to the board layout software, also by Cadence. Do you need that many inputs for an audio driver? What do you mean inputs? Basically, I'm getting to the point of, it's a FPGA isn't an audio driver. An FPGA is anything. It's a reconfigurable chip. You can think of it as an integrated circuit that you get to tell it with code what it is, which is great. It's hard once you get to the high levels, but it's great. Also, let me know about stream quality, because I have unlimited bandwidth in my lab, so I could stream basically whatever I wanted. Yeah. So I think that's pretty neat, because even for the 20 component little board that I did, it still couldn't route it on the first try. I had to manually move some of the traces, which I thought it was awful, but it was neat. It was a good learning experience. So Now imagine having to do that for, imagine having to do that for a motherboard. That sounds like it'd be bad. Because then you're not only talking about... So this was... The thing I did was a simple 2-layer board. It basically had a ground plane, and then you had your other plane. You can have PCBs that have like 7... They can have 7 different little planes to be on, and they're connected. They've got vias that put power down through all the planes and grounds through the planes. Man, that must make routing a nightmare. But yeah, that's pretty neat. Okay. All right, so what's going on here? What else are we doing? Do we want to go over a paper? Do we want to look at research stuff today? We can look at research stuff. Not my research stuff. My research stuff is in progress. I don't mind any of you guys stealing my ideas. Okay, research stuff. Let's go to a paper. Let's go to a recent paper. Recent papers are good. Let's go to this guy's paper. Guy from Princeton. I just read his paper the other week. I thought it was fairly interesting. Let's see. Where is it? There's his course. Where's his papers? I'll just look it up. Let's see. Yeah, so this David Winsloff guy, I think he worked on, so there was actually a really cool thing that Intel was working on. So Intel gets a lot of flack for being, behind the curve. Actually, no, this was Microsoft. Never mind. I'm not going to give Intel any credit. There's actually this very interesting thing that came out that was an alternative to x86 architecture, which is pretty interesting because Intel's downfall is that they made an architecture that they can't move away from because it's so highly optimized that even if there's another route that, could have better performance, then they still can't pursue it because, it's going to take so long to be as good as current processors. All right, let's see. I sent this out to my reading group. Let's see, ISCA reading group. Nope. A bunch of reschedules. Thursday this week. Okay. Hope. Has attachment. Okay. Reading group. There it is. Camouflage. Pretty interesting paper. Oh, this was from HPCA. That's it. HPCA is it's a performance on, or it's a conference on high performance computer architecture. It's pretty interesting. It's a good conference. It's not the best. Actually, that's not true. Depends who you ask. Where's my download button? There it is. Save file. Camouflage. Okay. Let's open. Let's see if I can remember how to do this. Because I think I have to... Oh, that's right. I have to use the top thing. File, annotate PDF. That's right. Let's go to downloads. Okay, here we go. We got a paper. Also, did you check to see if you have a low latency option? Maybe. I don't know. Hello there. Sour, not hardcore. Okay, so camouflage. All right. This is a paper from HPCA 2017, as it says at the top. This is a pretty interesting paper. So I work in the security area, so that's why this paper is interesting to me. So it's always nice to see us look at security papers. Sometimes security papers can be. So here's an interesting thing. So the Spectre and kind of meltdown vulnerabilities. So everyone kind of lost their minds over that. So why did they lose their minds? It's because it's something basically saying that here's a flaw that we can't fix with software because it's inherent in hardware. So, okay. That's bad. But here's the funny thing. The funny thing is that who cares if it's a fundamental flaw in hardware? Now, obviously it's a big deal, and that this is a problem based on, everyone focusing on performance, because performance is the bright and shiny, object that everyone chases. So no one cares about security. And where that's even more painfully apparent is in the software community, because if anything is a vulnerability, it's software. So there's so many research papers that are software fixes for security that never get implemented, and they have about a 1%, 2% hit on performance. But somebody talks about Spectre and Meltdown, which is a way harder of a thing to exploit, and all of a sudden people are immediately willing to accept a 30% hit on performance. Seems a little bit crazy to me. That doesn't seem like that makes much sense. Why are we gonna all of a sudden take a 30% hit in performance over when there's 1,000 other things? It's like locking the door when there's no windows or walls on your building. That doesn't make much sense. It's like drivers. Drivers are awful. GPU drivers are especially awful, but you can make the argument that no one makes secure GPU drivers because the hardware's not secure to begin with. So if it's already not secure in hardware, it doesn't matter if you make the drivers secure. Okay. Okay, because of their cloud VMs will lose business. So what's the argument for? It's easier to exploit software than hardware. So why would anyone try to exploit hardware? Just because you can exploit hardware doesn't mean it's a good mode of attack. There's 99% of papers that get published in security are, this is probably an exaggeration, a lot of papers that get published are just software security leaks because, hardware is something that's iterated on. Hardware is not something that moves very quickly because, the time it takes to, tape out a chip is way longer. If they don't patch it, all of their VMs are open to being read. I don't know if that's true. I don't know what isolation they have in there for different users in that virtual space. I mean, there's already stuff to attack stuff in the cloud anyway. There was a covert channel paper there was a big covert channels paper on that was fairly recent. There's all kinds of timing attacks. So the biggest exploit that people do right now with hardware exploits is timing attacks, because it turns out hardware is pretty predictable. Okay, I'm gonna get to this paper now because this paper is pretty interesting. So it's by these guys. These are the professors. Professors are usually last. on the paper. So let me so Pratik Mittal and David Winsloff. David Winsloff is an architecture guy, and these are grad students. He's an architecture guy. I don't know Pratik Mittal, or if I'm butchering that name, but yeah, he's an architecture guy. So I'm not surprised that this is a fairly architecture-heavy paper. So yeah, this paper is on reducing leaks based on timing side channel attacks. So if you don't know what a timing side channel attack is, well, they have this neat picture right here to show you. So, basically what happens is, if you've got, two different, if you've got co-scheduled VMs, and there's papers basically saying how you can, there's papers basically talking about how you can make VMs co-resident, and there's numerous strategies to do that. Even in Amazon, or in Amazon EC2, that's what most of these papers do. They prove that you can make co-resident VMs in Amazon EC2, and that's their cloud elastic compute service. So basically what this is saying is, okay, you have two things that are co-resident. Now, it's pretty obvious that if the bad guy decides, hey, I know what I'm going to do. I'm going to generate a bunch of predictable, consistently timed reads or writes or something, and put pressure on the memory system. Well, this guy over here, they're sharing the same memory system. They're shared resources. That's one of the interesting things in architecture, is that there's a lot of shared resources in systems, and how do you make shared resources secure? That's a problem. So basically, what this person can do is they can, periodically send the requests, and then, based upon the timing differences that they get between these requests, they can infer something about the distance between these requests, so they can get information about the access pattern of some other user, which that may seem like, well, great, what can you do with an access pattern? That's not very interesting, but there's a bunch of attacks on AES that are based upon this exact principle, that they're able to completely do a complete key recovery based upon simple timing information like this. So let's see. So what do they propose to stop this? So they want something with a predetermined distribution, which, it's one of these interesting things that I'm always a little confused of. And I think it's mainly the hardware people's fault, because the hardware does a certain thing and that thing has not changed. And so, there's a fairly big issue with the current architecture and moving forward with the security focus, because all these architectures were basically designed under the guise of, we have one person running something, and that person is probably not going to attack themselves with a malicious program. But now that we have, we have the cloud, all of a sudden, oh, we don't have that. We have, X amount of people on a single system, all sharing the same resources. And they've got some security things in place, but the overall system wasn't designed for that kind of sharing of people that are untrusted. So what do they want to do? So a predetermined distribution for security purposes. Basically, what they want to do is they want to make this consistent. They don't want this bad guy to be able to tell anything about this guy's access pattern, and so they want to service these requests in some predetermined fashion. Okay, so it works on requests and responses. I think it works the same way with both requests and responses, I think. It's complementary to ORAM, which are, it's this thing called Oblivious RAM. I had never heard of it. I don't think many people use this. Maybe in very high security sensitive. It's another security thing, but that's not what this paper is about. And it outperforms things by up to 50%, which is good. That's pretty good. Okay. So, introduction. Secure software and hardware have been proposed. Everything's bad. They don't prevent information leakage through side channel attacks caused by research sharing. So, Intel's TXT, which is their trusted execution technology, yep, doesn't help. Execute-only memory, Aegis, and Ascend. These are two things that they go into the paper that they define as they're research things, but this is something that they actually talk about in the paper that they compare against. Yeah, so they focus on two different points of attack. That's fine. This is really what they're focusing on, though. This graph here. And basically what they're saying is that these are all of their different, all the different protection mechanisms for, making consistent, read patterns where they're not leaking information about memory accesses. And basically the thing is they get a little bit better in performance with this very strict kind of isolation of mutual information. But, we want performance. And so this isn't scaled or anything. So, when they're saying a 50% improvement in performance over current methodologies, I forgot exactly what that meant compared to the baseline of, completely kind of, not completely trusted, but, they're not doing any protection things. But the problem is this overlap. You don't want this overlap. Because if there's overlap, that means there's shared resources, which means if there's shared resources, somebody's going to figure out how to exploit it. That's just a good rule of thumb. So, they've got the two things. They've got request camouflage. Request camouflage, and they've got response camouflage. And then bidirectional camouflage. Bidirectional is just these two together, like I said. Okay, so what do they do in this paper? Their main contributions. So their main contributions are the 3 hardware traffic shaping and generation mechanisms. Okay, it's really only 2, but I guess you can say that if you put the 2 things that you made together, it's 3. Sure. Camouflage protects timing information, not only in the memory system, but also in the shared channel between processor cores. Yep. I mean, if you order things in a certain way, you're going to get that protection, so that's not really that interesting. We leverage information theory. Okay, so this is part of the reason why they got in. They proved that it was secure. That's how you get an easy idea. Not an easy idea, but a fairly simple idea in. You prove that it works. Okay, we designed camouflage to provide a larger security and performance trade-off space. There's another thing. Not only do they have something that works, they have something that works that you can move around depending on what you want. Okay. Some latex stuff from earlier. Okay. So let's see. Okay, so here they're just kind of comparing what they want. So they've got this frequency-based one where here they're looking at the inner arrival times. And basically what's happening is because I think that they're only, they're only servicing within certain intervals, you end up with this huge spike at the end with long latency ones because you can't really account for bursty traffic that well. Here they're just doing them all in one time space. So this is bad for performance because it means you're not taking advantage of this entire early time. You're buffering them all and you're having to do them all at once. And so this is what they want. This is camouflage, basically, that they just want a consistent pattern that they're always servicing. So it always looks like this no matter what this input is. So, yep, that's fairly straightforward. I get it. Okay. Here's their design. Okay. So basically what they're doing is they're shoving something here by the last level cache before it gets to the network on chip and memory controller and DRAM. And then on the return path, they want to shape it at the memory controller from the other way, being serviced from DRAM. So you're protecting, you're protecting requests, and then you're also protecting, how you're protecting on the side of how users are generating requests, and you're also protecting on the side of how the DRAM is servicing these requests and how the memory controller is servicing these requests. Okay, that's okay. That's pretty neat. Architecture. So what do? So they give it a predetermined rate, or they give it a predetermined distribution, and they do this by generating fake requests, and they're basically shaping memory traffic. Okay. Yep, I think most people would be able to understand that. Basically what they're doing is they get something in and, any particular kind of distribution, and then they force it to fit another distribution. So how do they do this? I think they got a picture on the architecture. Here we go. Response queue. This is pretty much this is both sides, really. I'm pretty sure this is the same thing on both sides. So I think they have 3 circumstances here. So basically what happens is that things from the memory controller, they go down here and they fill up this buffer. And then what happens is the things that are in this buffer get serviced first, and they do this by having this number of credits. And what happens is if there's an unused amount of credits, they basically put fake responses in here. But I think this entire block here, this is used for, we'll just call that feedback. Actually, let's make that smaller. Yeah. So this is all feedback. So what I'm pretty sure that, what I remember from the paper, is that they track how many unused credits. So if they're continually not using credits, what they do is they send something back to the memory controller, and they actually change the distribution so that someone else can, take advantage, and they're not just servicing a bunch of fake requests. So fairly simple. And then, if they use up all the credits, the memory requests just get buffered. Okay. So buffer just means that they have to wait. Okay. Let's see. And so they even do some neat stuff in here. So this just kind of shows you what I'm talking about. This is actually this is good. So basically what happens is this is what they want it to look like. This is what it actually looks like. And so these are fake requests, these green things. And then they just pad. They just pad it. And so so you could ask, what is the opposite case where, instead, maybe instead of lacking one here, maybe it had an extra one here. So what I think would do is that so we'll just pretend that there's 2 here. And so here they added 1 fake request, but now we're up by 1 compared to the desired distribution. So what they're going to do with this is they're just going to cut it out, and they're just going to buffer it. And so they're just going to send that, in their next set of servicing. So what did they use to simulate this? They used SSIM and the DRAM simulator, DRAM Sim 2. 2 things that I've never used. SSIM is driven by the Gem 5 Alpha ISA. Okay. Gem 5 is a CPU simulator. It's a processor simulator. Very powerful. I think it was developed by Wisconsin. And they use the spec benchmark. Okay. And then they also wrote some Verilog to get the size estimates. So here's part of the reason why they got in. See this? See this? See this? See this? See this? Talking about Markov chains? See all those things? Do you know what that means? For a lot of architects, it means I'm not going to look at this because I'm an architect, not a mathematician. There's actually a great paper that I should probably pull up that's an even better example of this. So, yes, this is good. It's not terribly complex. It's just basic information theory stuff. But, you know, you're going to get some people in the review process that aren't going to look at this. That they're going to see this page of math and they go, I'll assume that you did your homework. So, it's not cheating, but that's how it works sometimes. Okay, some boring figures. Here we go. So, what they're basically saying is they're just doing tests here. This is what they want the distribution to look like. And then these are all the distributions of the spec 2006 benchmark suite. Okay. And here we go. Here's the actual interesting numbers. So the one on the far right is camouflaged, and the other two are temporal partitioning and fixed service with bank partitioning. So yeah, those it does better. It does a lot better. Will this ever be implemented? Absolutely not, because it has a performance hit. So why would they ever implement this? But they have performance increases over other state-of-the-art. It's hard for me to know what they mean by state-of-the-art, because state-of-the-art is usually not implemented. Here's something interesting. So here's a state-of-the-art is something that's usually just it's state-of-the-art in research. It's not state-of-the-art in applied, because most research ideas are never implemented. There's some things, but there's also the problem of you'll never know if it's implemented, because then it's intellectual property. Here's a funny thing about that. You ever wonder why those companies don't talk about their architecture? Because they're probably using architecture from research papers and not giving them credit. It's because you don't have to pay people. You don't have to pay people for their designs if you don't tell them you're using it. And it's really, really hard to figure out if they're using your designs. Okay, so here's an even, kind of cooler way to see, those types of, that figure that they had in the beginning. Let's see. So the figure that they had at the beginning, that was pretty interesting. So when we saw this, where some attacker is doing some consistent pattern of requests, so that's actually exactly what they're showing down here. This is that exact attack, pretty much. It's somebody's doing consistent memory reads or something, and they're trying to get information about what someone else is doing. And so you can see that there's this very consistent pattern that they can read from and get timing information from. But then after it, it's all swizzled, so you can't tell anything. Same thing here. It's all swizzled. You don't know what's real, what's fake. You don't know what timing to believe. There is no timing to believe, really. So this is a pretty cool way of visualizing something like this. So this is also probably a reason to get into a paper. If you can show something cool like this, and I know I say that it's cool, but trust me, it is. You just got to believe me on it. I know it looks like a barcode, but believe me, It's pretty interesting. Yeah, and that's pretty much it. So we find camouflage on average improves program performance by 1.5x, 1.12x, and 1.32x respectively. Now, over the other things. It doesn't improve performance. It improves performance over the other security things. It's still, if you look at the graphs from just a little bit earlier, it's still above 1. This is slowdown. So above 1 means you're slowing down. So it doesn't help overall performance. It helps performance if you're using something that's security related that is never implemented. But, there was actually an interesting talk in ISCA. ISCA's another computer architecture conference that talking about how we focused for really, really long on performance, and we let security fall to the wayside, and now we're only finally facing the consequences of something like that. So, yeah. But yeah, this is a pretty interesting paper. Oh, I know what I was going to show. I was going to show the paper that I know every single reviewer did not read this section of this paper. They did not read this section. I know that because I didn't read this section. I tried to read this section, but I refused. Let's see. Okay, here's the paper. This was from Micro, another architecture conference. It's another seemingly simple idea, but they proved that it worked. But I'm going to say that no reviewer read this paper completely. Or maybe one reviewer did, and they just believed them. That's what I'm going to say. That's my claim. Okay. Open. Annotate PDF. Discard. Let's see. 2040, 2115. That's the one. Okay. This one. The one with the cool title. RCool. Mitigating GPU timing attack via subwarp-based randomized coalescing techniques. Okay. That's kind of silly. It is kind of silly. But it's also true. Listen, so when you were a kid and you were reading some book and you came across a very hard word in the book, what do most people do? They use context clues and they figure out what it means, or they skip over it. One of those two things. So if you're in a research paper and you come across a section that you don't understand because it's something outside your area, what you typically do is context clues. The same kind of thing. If you're not dedicated to reviewing, and so what you do is, okay, they're trying to prove this. I'm gonna assume that all of this math proves this, which is not, you have to have some level of trust in these things, but are we ready for it though? Are we ready for the thing that every reviewer skipped? There we go. We're getting close. Oh, here we go. Here we go. We're getting there. Yep. Here we go. Yep. See this? Let's highlight some of this. Yeah. Let's use a red highlighter. Yeah. This. Nobody's reading this. Nobody's reading this. Nobody's reading this. Nobody's looking at. Nobody's going to go back and, try to remember what Sterling numbers are of the second kind. No one's going to. I can't imagine an architect going through this paper and getting to this section and going, I know what I'm going to do. I'm a professor and I have my professor duties. I have my lab to run. I have teaching I probably have to do. I have grants I have to write. I know what I'm going to do with my time. I'm going to have to learn all of this security theory and information theory for a paper I'm reviewing. I'm going to say no. I'm going to say they didn't do that. And then we get back to the pretty graphs that are in architecture papers. So that's what architects were great at two things in papers. So it's a great thing about architecture conferences. One, they're like 10 to 12 pages. It's not like, you have to write some 30, 40 page thing. 10 to 12 pages. That's great. And then the other thing is pretty pictures. We just have tons of graphs like this. Most architecture papers don't have this in them. Like, the most you'll get is maybe this is like the most math you'll get in a lot of architecture papers. You don't get a ton of math in architecture papers. You get a lot of pretty figures of, this is a coalescing unit for a GPU, and this is how they modified it with this subwarp ID. And what else do they have? They have things like this, talking about different methods for coalescing and what it looks like. And then pretty graphs like this, where they have a bunch of data points and then they mark out a pretty one. So yeah. And then usually maybe some code, depending on what type of paper it is, some code. But usually it's bar graphs and scatter plots and figures like this. But if you get this math in there, yeah, that's when you're cooking on the front burner. Okay. Okay. Well, that's about all I had prepared for this. Actually, that wasn't even prepared. Kind of just winged that. But, yeah. So, what did we learn today? Did we learn anything today? We learned that nobody reads math in security papers. Nope, that's wrong. In architecture papers. What else did we learn? We also learned that simple ideas can get into a conference with a simple idea if it works and if you can prove it works. And what else did we learn? We learned that I need to get better at writing on this tablet. Yeah. That's what we learned today. So we learned that nobody reads the math in architecture papers, that simple ideas can get into conferences, as long as you prove that it works. And that, yeah, I need to practice more with this Wacom. Wacom? Is it Wacom or Wacom? I don't know. I need to get better at writing with this tablet. But, yeah, that's pretty interesting. Let's see. All right. Next time. What do we want to do next time? Let's learn something interesting next time. Oh, yeah, demos. That's what I was going to do. Demos. So, what I can probably do is I can demo some cool things. So I can demo things like the Spectre attack and the Meltdown attack, and what else? Maybe not next time, but I can do that at some point. What else? Oh, I can do things like simulators. Most people have never seen what an architecture simulator looks like. And guess what? You're gonna be disappointed. It's a command line. It doesn't have options. You just source a config file and then you run your application. And then it just attaches it. This SO file just attaches itself to your app and runs. But hey, that's where your architectures come from. Okay. Well, that's all I have for today. So let's see some closing remarks on this wonderful Wednesday. So number one, thanks for stopping by. I appreciate it. When do you plan on streaming next? Probably tomorrow. I figure I'd probably make this 1 to 2 hours in the evening. Just something fun to do while I'm still at my lab. Let's see. Number two. I hope you learned something. And if you didn't, that's okay. If you didn't, just let me know, and I'd be happy to give you a fun fact. And then 3, I hope you have a great evening. Let's see. Wait, what about Siemens? Let's see. It's going to be hard for me to follow because of time zones, but I'll try anyway. Well, that's okay. I don't need to stream only in the evening. I can do some earlier streams. Not in the afternoon or something because I'm doing this in my lab. I can do some early morning though. I can be your teaching in the morning. What are we talking about Siemens for? I've worked with Siemens before, doing PLCs, programmable logic controllers. Oh, it's 327, so that means you're... Oh, what is that? That's like GMT-ish. Yeah. Okay. Well, that should be fine then. Okay. Yeah, I'm always off by a time zone. It's new. I'm in the East Coast now, so... I shouldn't say I'm in the East Coast. I'm in East Coast time zone now. Yeah, that's about... Yeah, +1. Yeah. Because I'm minus... I know normally I'm -5, but I don't know how daylight savings works because it's stupid. Okay, so yeah, 6 hours. Yeah, I must be -5. Okay. Well, if there's no questions or anything, I'll wait a couple of seconds, see if there's anyone who wants to say anything. Anyone has any last remarks or questions or things that they want addressed. Or if they have any, anything that they want to see on the stream. Maybe they want to see a demo of how to do something. I'm not opposed to that. If it's something computer science related, you're probably better off finding someone that's a computer scientist. But I do that kind of work. Okay. Well, like I said, thanks for dropping by and have a wonderful evening. Adios.